Hello, everyone, and welcome to yet another fabulous webinar that it is going to be hosted through the auspices of SAAO and SciFest, and the South African Astronomical Observatory are celebrating 200 years. And let me tell you, this is probably one of the most exciting relationships I've seen, where SAAO and SciFest have bonded and are producing the most incredible content, the most wonderful presentations, where you, the audience, gets to interact with some of the most incredible speakers, and not just shabby ones. We're talking high-notch speakers here. So you certainly want to pay attention to today's seminar, because I'm very excited to announce that our guest for today will be Dr. Val Musisami, and he's got a very long CV, so I'm just going to pick at a couple of the highlights that I thought I would mention, because I would rather that he spend more time on his presentation and give you the chance to interact and ask questions about what he does. So Dr. Val Musisami, as of the January 2017, I believe, he was appointed the Chief Executive Officer of SANSA, which is the South African National Space Agency. We do have a space agency, in case you did not know that. And he is currently a member of the South African Council for Space Affairs. I wasn't even aware that we had a council for space affairs. And he is the Vice President of the International Astronautic Federation, the IAF. He has been recently inducted as an academic, or it says academician, it almost sounds like an academic and a magician together, of the International Academy of Astronautics, and he sits on the advisory boards of the Space Generation Advisory Council and the UAE's International Space Congress. I mean, that was just a small taste. If I had to go through what he has done just to get there, it would blow your mind. So let me tell you that Dr. Val is certainly very qualified to be chatting to you about our topic, which is going to be making sense of our world through space science and technology. So with that introduction, I'm going to hand over to Dr. Val, and he is going to wow you with his presentation.
Thank you, Sherman. And thank you for the honor of making this presentation. Just relatively speaking, SANSA will be celebrating its 10-year anniversary. So in relation, I think SAO is our great-great-great-great-grandmother. You're celebrating 200 years. So I thought it was opportune to take this opportunity to present, as you indicated, what does space science and technology means for our everyday existence. And I think this is something that's very necessary, because sometimes we have a misconception of what it actually means. And when we talk about space, people normally think about the moon and Mars. But I want to bring it back to Earth, and that's why I think this conversation is so critically important with the public. Just by the way, anything that you observe around you is made possible through this particular slide. So what you see, what you hear, and what you feel comes from the electromagnetic spectrum. So just to put this in context, everything we see and hear is because of what we call electromagnetic waves. So if you go on the left-hand side of this slide, these are very short wavelengths. And that part of the spectrum is where we have the high energy waves. So for example, your gamma rays come from the universe, from the sun, and so on. So they're very high intensity or energy waves. If you ever went to a doctor's office and with possibly a broken limb, they would send you for an X-ray. And that is also very high energy electromagnetic waves. So high that it can actually penetrate your skin, and you can capture the image of the bone. And that allows you to see whether the bone is broken or not. If you go to your right-hand side, where we're talking about the long wavelengths and lower energy, here we're talking about radio waves, waves that we listen to, for example, when you listen to the radio or TV for that matter. And then in the middle, somewhere in the middle, we have what is called the visible light. Now, that's a very narrow segment of the electromagnetic spectrum, but this part of the spectrum allows you and I to see. And so that's expanded at the bottom, and that runs forward from between 400 nanometers and 700 nanometers. And so that's what we can see. So the rest of the electromagnetic spectrum, we cannot see. We can hear parts of it. For example, the infrared, we cannot see that. And this slide is very important in the context of this presentation. I'll come back to why. So I want to give you a sense from a very basic perspective on how satellites get to be in orbit. So can you imagine yourself if you were asked to throw a ball? And so if you did that and you threw it with so much of energy that it landed a certain distance away from you, I then asked you, can you please throw the ball even further away? So what you would do is you'd expend more energy, and that will allow the ball to land even further. Now, can you imagine if I keep asking you to do that and increase the distance at which you throw the ball? Now, this is the fundamental principle of what is called the Newton gun. If I can explain this to you, if you stand on the top of a mountain, and if you throw, let's say, this ball, it falls a distance A. Then I ask you to throw it a little harder, it falls distance B. Then I say, please, can you throw it even harder? And it starts to move along the trajectory C. Now, you can imagine, you can see that the ball is trying to fall towards the Earth, but because the Earth is spherical and is curved, it never quite falls into the Earth. So what actually happens if you throw it with enough energy, you're throwing it into space, it's trying to fall towards the Earth, but because the Earth is curving inwards, it never touches the Earth. So that's essentially how we put a satellite into orbit. And you can throw this satellite into different orbits. So just to put that into perspective, we have, if we take orbit D, for example, you can have what is called low Earth orbit. So effectively, the satellite is orbiting around the Earth between 400 and 600 kilometers in altitude. So that's 400 and 600 kilometers above us. And the speed at which that satellite comes past us is around 27,000 kilometers per hour. Okay, so you can imagine if a satellite is coming from the direction of Europe and it passes South Africa and then disappears down in the South Pole. Effectively, if you have to travel between Pretoria and Cape Town, you could essentially take 4 to 5 seconds to move from Pretoria to Cape Town. And if you had to take how much would pass one revolution around the Earth, meaning going from one pole back to the same pole, it takes around 90 minutes, between 90 and 120 minutes. If you look at trajectory E, you can throw it even further than the low Earth orbit. And this is where the whole idea of a geosynchronous or geostationary orbit comes from. So a geostationary orbit is around 36,000 kilometers above the Earth's surface. And the satellite is traveling around 11,000 kilometers per hour. So the further away you throw the satellite, the slower it moves compared to when you throw it closer to the Earth. And at the geostationary orbit around 36,000 kilometers, the periodicity, that means the time it goes around the Earth in 24 hours. So effectively, as the Earth is rotating in 24 hours, the satellite is stationary above the Earth's surface. So that's why we call it geostationary. Okay. And this will become important and evident as to why I'm putting this up. So this is essentially what happens, is you have these satellites that are continuously orbiting the Earth. And we use that to our advantage in terms of putting payloads on these satellites. So you could have optical images, payloads that take imagery of the Earth. You could have telecommunications where you can talk to the satellite and pass broadcasting signals to. And you can have satellites that look at our weather patterns. You can have satellites that can sense how much of pollution is in our atmosphere. So you can do a lot of measurements from space that you can't normally do from the Earth. And what's important from a satellite perspective is you get what is called a systematic coverage of the Earth. So if you take an observation from the surface of the Earth, you can only take the observation at one point of where the instrument is. Whereas with the satellite, it's continuously orbiting, so you can take observations of the entire Earth just on that one satellite, but it will take you time to cover the entire Earth. So just from a satellite perspective, this is what the satellites look like. So from a South African perspective, we have two satellite classes that we are working on. We have a CubeSat. So on your left-hand side is a CubeSat. Now, just to give you a sense of what a cube looks like, it's a satellite, or 1U is a satellite that's 10 centimeters by 10 centimeters by 10 centimeters. So it's almost 2 or 3 times bigger than your magic cube that you have at home probably. So what you see here is a 3U cube. So that's 30 centimeters by 10 centimeters by 10 centimeters. And that's almost the size of a bread loaf. So this particular satellite, for example, was launched in 2018, and it can tell you all of the ships along our coastline, which is 3,200 kilometers on one satellite pass. So it can tell you each and every ship that is on our coastline. That's the value proposition we get from these kinds of satellites. These are satellites also used for scientific experiments. The satellite on the right is called a small sat. So that satellite can be anywhere between 200 and 400 kilograms. So the one you see on the right is one that we were busy developing, which we are currently trying to finalize. But this is an Earth observation satellite. So it has a camera system on board, which takes images of the Earth. So if it is orbiting over South Africa, it will take an image, a strip of images across South Africa as it passes by. So how do we get the satellite into orbit? These satellites that I've just mentioned, well, you put them on the rocket. So effectively where the satellite sits is at the top of the rocket, the nose cone of the rocket itself. So what actually happens, you fire up a satellite and you launch it into space. And if you watch the satellite trajectory, it's sort of launched vertically. But as it goes higher, it sort of bends and it follows that parabolic trajectory I showed you, where the little boy was throwing the ball. So it follows that kind of trajectory before it gets into space. So what actually happens when it gets into space is the nose cone, or what we call the flarings, they are ejected outwards. And at the top is where the satellite sits. And this is where the satellite is ejected from the rocket and is thrown into space. And then it goes into this orbit that I've mentioned and I've described to you as it's falling towards the Earth. And then you have to stabilize the satellite so that the camera systems are all pointing toward the Earth all over in space. So you have stabilizers, sort of gyroscopes that help you to control the stabilization. We normally talk about 3-axis stabilization, meaning that the camera system on this satellite will always be facing downwards as the satellite is orbiting. Now, what does SANSA has to do with this particular aspect of launching? It's very important because we play a very critical role in the global launch services. So if you take the launches that happens from the US, so there's 2 sites in the United States where launches take place from. One is called Vandenberg, the other one is Cape Canaveral. So when a rocket is launched from those 2 sites, if you follow the red dotted line from those 2 sites, they come over this circle called HPK. HPK is Hartbeespoort. That's where SANSA has its space ground station operations. And what actually happened is when that launch vehicle comes over Africa or the HPK site, the Americans cannot see it. The same happens from French Guiana. This is a site used by the Europeans for the European launches, like the Ariane rockets. When it comes over Africa, it comes over the HPK site. So guess what? We take control over those launch vehicles and we carry on with the launch services or support. Now, this is very important because that it helps to keep continuous control of the launch sequence as it starts to unfold. So any launch that you see that's happening from Vandenberg, Cape Canaveral, or French Guiana, we are supporting it from SANSA perspective. And since the last 20, 30 years, we've done over 500. I think we're getting close to 600 launches. Okay. And what's also important is the ejection of those satellites that normally happen over our footprint. So we get the opportunity of switching on the satellites, testing the satellites, and then passing it on to the owner. So we do the launch supports, and then we also support the testing of the satellites itself and switching them on. So we play a very critical role for these launch services and these satellite services. There's another role that the HPK station plays. So as I said, when you launch a satellite into orbit, the satellite is making observations, is collecting data. It can be optical images, it can be what we call synthetic aperture radar or communications, or it's picking signals from the ships. So it's collecting data, but the data needs to come back down. So this is where we provide what is called a telemetry downlink. So you have these antennas that are talking to the satellites and bringing the data down. The second thing these antennas do is that you can update. So there's a lot of software that's embedded inside of the satellite that helps it to perform certain functions. And if you pick up certain problems, for example, you can update the software. So as the satellite comes through or past South Africa, you can issue the commands and upload new software, and you can do all sorts of fancy updates on the satellite itself. So you're commanding the satellite, and then you're also bringing the data back. So to do that, we have a number of these antennas on the ground. So at the moment, we're speaking around 50 antennas that we have on site. Now, at the moment, we are also building what is called a teleports services. So we are building around 20 new antennas, which will come in operations by the end of this year. And these 20 antennas will be talking to close to 900 satellites at a time. Now, these satellites, these 900 satellites, will provide global internet connectivity. This means that if you are even in a rural area, you could have access to internet with an antenna that is the size of your teacup. So these are new technologies that are coming through. So by the end of this year, we'll have about 70 odd antennas in our ground station. So it's a 24/7 operations. There are staff on this site 24 hours a day, 7 days a week, and 366 or 65 days a year. So this is a full-time operation. So just to take you into the perspective of how one uses these slides. So I spoke about the electromagnetic spectrum. So if you look at sunlight, sunlight is made up of what we call white light. But if you break up white light, if you actually had an experiment done at school where you pass light through a prism, you see all of the colors of the rainbow in the white light or in the sunlight. Okay? So effectively, the light that's coming from the sun has all of the colors of the spectrum. So you could have red, blue, and green. So I'm giving you an example here where the sunlight is reflecting off a tree. And then as it's reflected and gets back out to space, a satellite will capture the image. But if you look at the leaf just above the tree, what's actually happening at the micro level is the green part of that spectrum is reflected off the leaf, whereas the red and the blue are actually absorbed by the leaf. So that explains why the leaf appears green and not blue or red, is because it's reflecting green light or green part of the spectrum and absorbing the rest. So that is what the satellite is seeing, is the part of the spectrum that is actually reflected, and the rest is absorbed by whatever structure is on the ground. Now this is very important. So just to give you a sense of how this would work in practical terms. Now don't get alarmed by this graph. I'll explain this to you. If you look at your left-hand side, that little blip at the bottom, that blip is all what you and I can see on your left-hand side at 500 nanometers. From this part, so let me just put this up. So this is all we can see, the one in light gray, green, sort of. The rest of the spectrum, you and I cannot see. This is now going into what is called the infrared part of the spectrum. So if I just show you the spectrum, if you look at the parts that we cannot see in the infrared, at the near infrared part, in the short wavelength infrared, that part of the structure of the spectrum tells you the structure of the plants. So by looking at this part of the spectrum, you could see or tell whether this is a maize plant, whether this is a wheat plant, or whether this is just grass. So you can differentiate from space just by looking at a curve like this, what type of crop is in the farm. If you go further to the right, this part of the spectrum tells you how much of water is in the plant. So one day if you find the peak is very high, means it has a lot of water. If the peak gets very low, means there's low water. And if the structure of the cell changes, you could pick up there's diseases coming in the plant. So this kind of information you and I cannot see. And in fact, the effects that are coming through in this part of the spectrum happens way before we see the visible effects on the visible part of the spectrum, before we actually see it. So we use this kind of information to tell the farmer when to fertilize, how much of water to apply, because his plants are becoming dry because there's drought or what have you. So we use this for what is called precision farming. To give you another example, you could be using this part of the spectrum. So one of the things that's very useful about the satellite is it's placed in what is called sun synchronous orbit. That means that the satellite comes through at the same time every day. So that satellite will come through, for example, at 9 o'clock every morning, like clockwork. So what it allows you to do is to take an image of, let's say, a water body, let's say Midmar Dam. Every day you're kind of looking at this dam, and suddenly the structure or this structure changes. You can immediately figure out that something has happened in the water body. And if you go and look, you might find there's cholera coming through. So there might be diseases coming through. And that you can pick up before you actually see it visibly. So you can do something about these things. So this is a very powerful tool, and this is what governments, departments use to make decisions on our environment. And there's a whole host of applications that one can use. And just to give you a sense, there's a satellite imagery on the left-hand side. It's sort of colored in. And if you look at the red patches, that tells you the plants are stressed. And if you go into the farm, which is on the right-hand side, you can see the plants are actually dried. So you can verify or validate the image on your left-hand side. So as I said, this is a very so the other aspect, so just on this slide that I've just left, this is very important for food security in terms of what you and I eat every day, to make sure that the crop production is kept alive and the crop yield is optimized through these kind of applications. The other application is what I call satellite communications. Remember I said the geostationary orbit, which is 36,000 kilometers. So the way this works is you have a transmitting station where the event is actually happening. That signal is uplinked or transmitted to a satellite, and then the satellite transmits or broadcasts that signal to the Earth receiving station. So just to give you an example, if you're watching soccer or let's say Formula One over the weekend, and it's a live event, so how does it come to your satellite TV? Is the signal is transmitted to the satellite, which is 36,000 kilometers. The satellite then streams the signal back to Earth. And if you've ever seen satellite TV dishes, have you ever wondered why all of these dishes actually point in the same direction? The reason for that is they are pointing to the same satellite. That satellite is 36,000 kilometers away. And there's a few millisecond delay. Sometimes you'll notice there will be a live interview happening, and the person on the other side that's being interviewed will wait a few seconds or milliseconds delay before they start answering. That's because the signal is going to the satellite, which is 36,000 kilometers, and coming back another 36,000 kilometers at the speed of light. So there is a slight delay. Okay, so telecommunications is made possible through satellites. Navigation and positioning. So if you're looking at, let's say you've got a cell phone and you're using GPS to go from the place where you reside to, let's say, a destination where you want to get to. So you use Google Maps or whatever application, TomTom, on your phone. What is actually happening is there are satellites. You need, in any one constellation, at least 24 satellites at any time to be orbiting. But your phone needs to be speaking to at least 3 or more satellites at any one time. So the way this works is the satellite has very accurate timing signals coming through. So they have on board what is called atomic clocks, which gives very accurate timing signals. So you can figure out or calculate how much time it takes for a signal to leave one satellite before it reaches your phone. And if you do that for 3 satellites, which are in different parts of the orbit, you can then triangulate and calculate exactly where you are on the Earth. So this is the basic principle you use for navigation and positioning on the Earth's surface. You actually need 3 or more satellite signals. The one problem we have, though, is that with this setup, your signal error that you get from the GPS can be out between 5 to 10 meters. So if you look at all the red dots on your right-hand side, you can see there's a spread of the signal itself. And that might be problematic. For example, if you want to land an aircraft in a very rural place. So for example, if you're talking astronomy, if you travel to Carnarvon, you land in a sort of a makeshift airfield. You cannot afford to be out by 5 meters from the runway. You'll actually land on the side. And I'm not sure if you've ever experienced using your GPS and you look at it and you see you're actually driving on the side of the road. That's because there's an error in the signal. So what we are doing as SANSA is we have tested a system called the satellite-based augmentation system, which improves the accuracy and it limits it to the green area. So you can limit it to under 1 meter. And this application has huge benefits. So for example, Statistics South Africa wants to do statistics on how many people live in each household. And when you get to the informal settlements, as an example, we don't have address boxes. So if you have a location-based service that can give you the location of a dwelling within a meter, then you can accurately mark each house with an address, and then that can be used for statistical purposes. So this is a very powerful tool that we will be introducing in the next few years. I should also mention in the next 3 to 4 years, we'll be launching about 6 satellites, and that will also give us way more data that we are currently getting at the moment. And every day we download data from 15 to 18 satellites that goes past. And by the way, the satellites, as they come, as I said, from the direction of Europe and goes past into Antarctica, it takes effectively 2 minutes for that satellite to pass us by, to get the images, download it before we talk to the satellite and before we can't see it. So it moves very fast. And so we're upgrading even our antenna systems as well. The last area I want to talk about is called space science. Now, this is very interesting because the sun is continuously spewing out what we call radiation or plasma. And plasma is what we refer to as ionized particles. So in school, you'll probably learn about electrons and ions. So that's what's actually coming out of the sun. On a quiet day when nothing is happening, the velocity of that plasma that's coming towards the Earth is about 400 kilometers per second. Okay, so you could be in from Pretoria to Cape Town in 3 to 4 seconds as well. So it's coming through very quickly. But we also have events on the sun that happens, like what you see here is called coronal mass ejections. So there's excessive plasma that's emitted from the surface of the sun. And when that happens, your velocity of that plasma can go up to 800 to 1,000 kilometers per second if it's a very disturbed event. The only thing that's protecting us from the sun's radiation or that plasma is the Earth's magnetic field. If the Earth did not have a magnetic field, you and I would not exist today. We would not be here on Earth, because that magnetic field prevents that radiation from hitting us directly, which would kill us. Because radiation, actually, if it hits your skin, damages the cell. So it will kill off the cells on your skin, for example. So the Earth's magnetic field is very, very important for protecting us. And this is one of the reasons why we monitor the sun, because it has an effect on the equipment that we use on the ground. So we try to measure what's happening in space. We have a lot of infrastructure or equipment on the ground. We also have a base in Antarctica, and 80% of what's done in Antarctica is space physics related. Because remember, the Earth's magnetic field, they start from the magnetic pole and they end in the magnetic pole. They start in the South Pole and end in the North Pole. So any disturbance that's happening out in space, they get trapped along the magnetic field lines, and your magnetic poles, or your South Pole and your North Pole, acts as a natural observatory to know and figure out what's happening in space. So for example, when energy is dumped along the magnetic field lines into the polar regions, you get these green squiggly lines in the sky, which we call aurora. And that's because there's energetic particles getting into the ionosphere. And what you see is excitation of the oxygen atoms that's in the ionosphere. When you see it sort of pinkish, it means that it's exciting the nitrogen atoms in the ionosphere. So that's a natural observatory we put our scientists and engineers down. So we leave our engineers and scientists, we take them by ship, we drop them off, and we forget about them for 14 months. And they run these experiments, and we collect the data, and we bring them back, and we send a new crew. So we are also building a new space weather center, which is costing us about 100 million rands at the moment, which we are busy constructing. And this is very important because there's a new regulations that from the Civil Aviation Organization that says that every time a pilot takes off, they have to include space weather information. This was as of November last year. And the reason for that is that when a pilot is flying a plane, they communicate to the ground station by what is called high frequency radar signals or radio frequency transmission. And the way that works is the pilot, when they speak, they're transmitting a signal which hits the ionosphere and then reaches the ground station. But what actually happens when the sun gets very active, you have excessive radiation in the ionosphere, and the signal is atmosphere. It doesn't go to the, so you can't hear the pilot anymore. So you get what is called a communications blackout. The second thing that happens is the pilot uses navigation or global navigation satellite services. So they need these satellites to be able to figure out where they're flying. And during these active events, that signal from that satellite doesn't come through to the cockpit. So the pilot doesn't know where he or she is flying. So you lose sense of navigation. The third thing that happens here, if you're flying at higher altitudes, you get excessive radiation, and you could get radiation, higher doses of radiation. And it's even worse if you're traveling between South Africa or Southern Africa and South America. There's a region between Southern Africa and South America called the South Atlantic Anomaly, where the magnetic field is so weak that the radiation comes right through. And if you're flying from, let's say, South Africa to Brazil during an active event, you could get excessive radiation, and that could kill off some of the cells. And for aviation safety, you could say to the pilot, you're not allowed to fly now because there's a storm coming. So this has huge implications, and we will be providing this data in the next few years to the entire African continent. So I just wanted to give you a sense of how important space science and technology is for our everyday life. It's important to make sense of the farming, information to the farmers so that we have food on the table. It's important because we are able to watch live events like sporting events, live news broadcasts. It's important to us because we can understand the space environment and how it affects those technologies. It's important to us because it allows us to navigate on the Earth's surface using GPS. And all of this comes from space technology. And with this perspective, I thought it would be important for you to understand that you and I cannot exist without space technology. If you ever went into a bank to do an ATM transaction, for example, that transaction is going through a telecom satellite. The timing signal on that slip of paper that you receive, that receipt, comes from a navigation satellite. So everything, the transactions, all of that happens through satellite technology. So I just wanted to demonstrate to you how powerful space science and technology is and how it is empowering you and I and ensuring the modern day lifestyle that we are used to here in South Africa. Thank you for your attention.
Wow, that was incredibly informative. And what I found interesting is that a couple of questions were coming through and you were already answering those questions as your presentation was going on. But don't think I'm going to make it easy for you. I will certainly, let me see, there we go. Your presentation is out of the way. I'm going to start to ask you a couple of questions, but I'm going to throw my first one at you. You mentioned all the positives. It's wonderful that we have agriculture being monitored from space. It's wonderful that we can communicate and watch live TV and news. It's wonderful that we can work out which path our airplanes should take to make sure that our journeys are safe. But then what about the big brother aspect?
Yeah.
There is a concern that, for example, if you have access to live satellite feeds, you could watch me in my garden without my knowledge. And there's obviously a military factor to that.
Yeah.
So how do you mitigate, or well, maybe not even mitigate? I mean, what are your comments towards the fact that, yes, there are many great spin-offs to satellite technology, but there might be one or two that are slightly nefarious? Well, what are your views on that?
No, thanks, Steve. I think this is a very important question, and it actually demonstrates why you actually need your own technology rather than relying on foreign capabilities. Okay. Just to put this in perspective, it's a very expensive business to be in. So to manufacture one satellite can cost you anything between 200 to 600 million rands. And if you're looking at a telecom satellite, telecommunications satellite, that's around maybe 4 to 5 billion rands for one satellite, which lasts about 15 years or so. And the reason why we need this capability, exactly to your point, if you didn't have this capabilities and you relied on foreign capacity of your environment, okay, so you can pick up the mining potential in your backyard using these satellites. So you could look at the geostructure and you can figure out, okay, here I think there's a gold deposit, or and so on. Because if you didn't have the satellites, then your foreign competitor knows what's in your backyard. And then you see foreign investments flowing in that wants to capitalize on those resources. And you see this happening all over the world, especially in Africa. How does a foreign nation or country know that there's oil reserves in our coastline before South Africa knows it? It's coming from satellites. So unless you have that technology yourself and can figure out that this is what's in my backyard, then I can protect it and I can utilize it for economic and social benefit. So it's very important to avert this big brother. It's real, it's there. So we need to ensure the integrity of the data is that we have full control. So space is also intended for national security, to protect our resources. I mentioned the one example of this little CubeSat that's being able to pick up all of the shipping, the ships that are on our shoreline. What we do is, I've also very briefly mentioned synthetic aperture radar. So the difference between an optical satellite and a synthetic aperture radar, The optical satellite collects photons, like a camera. The synthetic aperture radar is an active sensor. It pushes a signal and it looks at the reflected signal. So that signal can cut through cloud systems and so on. So even on a cloudy day, you can see right through. So what we do is we capture all the signals and we overlay it with these images. And what you find very often, you will find a ship that does not have its transponder on, but you can see it. And then you know it's a rogue ship. And what we do is we send our Navy through and we find illegal shipping vessels that are actually taking fish off our oceans. We've tracked one of those ships without the transponders on from South America to Port Elizabeth that had drugs on board. And you can catch all of these illegal activities by using satellites. And this is, as I said, is for national security, and so that we don't become reliant on Big Brother to give us information, which can be filtered through to us as well. So it's very important. There's another negative side to space, which I didn't mention, is space debris. So at the moment, there's lots of debris, little pieces that are more than 5 centimeters, and we're looking at about 40,000 or so of those floating in space. And because of the velocity at which they move, if they hit a satellite, they can destroy a satellite. So we are busy looking at guidelines in terms of protecting the space environment and using it optimally as well. So there's all sorts of measures coming through in terms of the next generation of satellites being launched that we protect that environment. Thanks, Steve.
Sure. All right. I've got a whole bunch, but I need to be fair. I need to ask some of the questions from the audience. Ludovica would like to know, are satellites just, oh, well, he wanted to know, I'll ask his other question, how much does it cost to launch a CubeSat satellite?
So the CubeSat satellite, if you had to manufacture CubeSat satellite, it depends on the mission. Okay, so just to give you a sense, we will be launching 3 more satellites early next year for the ship detection. This now gives us real time. Those 3 satellites together with the cost of launch is about 27 million rands. So the smaller satellites are, relatively speaking, not that expensive. But when you go to the big satellite that I spoke about, as I said, that could be about 400, 600 million rands, depending on the mission that you're looking at, because there's a lot of research and development that goes through. If you're wanting to launch a satellite, you're paying about $10,000 per kilogram to launch a satellite. So launching is not cheap either.
Sure. I mean, I'll just order 5 or 6. I mean, that's not that expensive. But then if that is the case, then do you agree that a private person could quite easily fund, and I'm not going to mention any names in case their names rhyme with Usk, but there are some people in the world who have got their own money and are launching a series of satellites. It rhymes with R-Link, but I won't say who. And I mean, there might be some South Africans who've got some spare cash that would like to launch their own satellites. Is there some sort of ruling against who can launch satellites, and how do you police that?
Yes, so there is a ruling. There's a global platform called the United Nations Office for Outer Space Affairs. There's the United Nations Committee for the Peaceful Uses of Outer Space. So many of the countries that have space programs sign up to these treaties and conventions. So you have the Outer Space Treaty as an example. And so South Africa has ratified all of these agreements, these treaties and conventions. And this is where you set up the South African Council for Space Affairs, which is a regulatory body. So if you want to launch a satellite in your private capacity, you have to seek a license from the regulatory body. And the reason for that is that even in your private capacity, if you launch a satellite, if something goes wrong, if that satellite falls on somebody's head, let's say in Europe somewhere, South Africa as a country is responsible. So the government has to regulate the liability if something goes wrong. And there's a formal process by which you have to go through. So even private individuals in the US or wherever wanting to launch the satellites have to follow the regulatory process. Thanks, Shem.
Sure. Zetu wants to know, is there a way to reduce radiation? So, for example, if the aircraft was passing the South Atlantic anomaly, and you can obviously identify that there is going to be an abundance of radiation, you would obviously just tell them to avoid the flight. But is there a way to mitigate against that radiation? Do we start putting in materials on planes that absorb radiation, for example?
Yeah. So as I indicated in my presentation, the only thing that's protecting us is the Earth's magnetic field. So I suppose from a practical sense, you could say, yes, why not put a current loop around the aircraft structure to create a magnetic field? But that could be very expensive and impractical. So practically, yes, but very expensive. So it doesn't make sense. So you'd rather ground the aircraft and delay the flight, which is much more cost effective. This is also another problem, by the way. The missions that are going to Mars, Mars does not have a magnetic field. So if you're going to go to Mars, you have a problem. There's no protection against radiation. So they're looking at other interventions of how they can shield whoever is going to be landing, the astronauts that are going to Mars, to protect them against radiation. So there are developments underway in terms of kind of protection measures against radiation. So it is possible, but it's expensive at the moment. But there are new developments happening at the same time.
Now, Sharid says that SANSA is allegedly partnering with NASA. And if this is the case, what is going on and what is this relationship all about?
Yes, so we signed an agreement with NASA in February of this year. There was a team that came out. And so what we are exploring is setting up what is called a deep space network in South Africa. So just to give you a sense, when you're launching a mission to the moon, okay, you need to communicate with that spacecraft continuously. So the US will have a deep space network. So these are dishes that are about 30-meter diameter. So they are huge dishes. And they are talking to the spacecraft. But as the US, for example, as the Earth rotates, they get out of view, and there will be a site. The next site that comes through is maybe Australia. And then there's the third DSN, which is in Spain. So there's 3 deep space networks: Australia, Goldstone in the US, and there's one in Spain. So we're looking at hosting the 4th deep space network here in South Africa as redundancy, both in terms of latitude and longitude. And that's looking very promising. So that means we will be supporting those missions to the moon, back to the moon, and even the Mars missions in future. What I should also mention, and this is probably not well known, and there's a link to astronomy, in the lead up to the Apollo mission, there was a number of missions that took place, like the Ranger missions, the Orbiter mission, so the moon to actually see what was on the moon, and they did some ranging, hyperspectral imaging on the moon. All of those missions were supported by South Africa. So NASA used to have a base here. In fact, it's within SANSA. It's called the mini track. So since before the Apollo missions, we were supporting. There were only 3 stations: Australia, South Africa, and the US that were talking to those missions. And NASA pulled out in 1974 because of the political issues, the instability that we had of apartheid and so on. So now, but we've turned that deep space network into a radio astronomy telescope. And this is where the South African Sarau, the Hartbees took radio astronomical telescope. That is the telescope that was used for the deep space missions. So we have the capability, we have the reputation, we've been supporting a lot of those missions. So we have the technical capability, which allows us to have this conversation with NASA, which is actually looking very promising.
That is awesome. That is awesome. Now, this one comes from Camille. It says, as a Denel Space Tech employee who is proud to be working on EOSat-1, in the light of the other African nations like Egypt, Ethiopia, Nigeria ramping up their presence in the space industry, what measures are being taken to ensure that South Africa continues to grow its space heritage as a leader on the continent. And of course, I mean, that's going to be critical for you as the CEO of SANSA. It's not just about collaboration, but it's to make sure that you're an industry leader.
Yes. So there's a couple of things that are happening at this moment in time, Steve. So what we are talking about now is another 4.5 billion rand investment for the next 3 years to build what is called the Space Infrastructure Hub. And this is looking at half a dozen satellites, looking at upgrading our ground station, our data segment. So once you get the data through, it'll be on a cloud platform. We're having a new system, and the astronomers know what we mean by data cube, where you stack the data in a certain way, and you can extract the data within a few hours as opposed to a few months. And then we're getting the industry to help us build products and services. So the industry is going to be heavily involved in the building up of the value chain. I should also mention, I'm not trying to be complacent about this point, but all of the other African countries, when they talk about a satellite, they go out and procure a satellite. There's some countries that are building capabilities locally, engineering capabilities. But to date, I can safely say that South Africa is the only country that can design, manufacture, and operate a satellite without any external assistance. Most of the other countries are actually going out. And so I think we have the competitive advantage. And what the Space Infrastructure Hub helps us to do is to leverage on that advantage and take it even further in terms of building that capacity.
Okay, so Ludovica wanted to know, and I want to add to that, are we planning to start launching rockets from South Africa? And why don't we have an astronaut call?
Yeah. So just on the rockets side, this is also a very expensive business. And I think the current economic climate is working against us from that perspective. But what I should mention is that the Department of Science and Innovation have set up a working group to explore this opportunity, because you'll recall that South Africa did have launch capabilities in the late 80s. In fact, there were 3 successful suborbital launches from South Africa in the 89, sort of 90. And so the capability for building rocket vehicles or launches exists in South Africa. So we just have to be mindful that that capability does not retire out of the system as well. And so there is a working group that's looking at the launch capabilities, but as I said, it's very expensive. So it has to be done for strategic imperatives. The second question around the astronaut call, the cost of launching one astronaut into the International Space Station, let's say for 5 days, is $78 million. That's the ticket to ride. That's over R1 billion for one astronaut. If we had to do that, we have to do it based on a science case rather than a happy ride. So it's very expensive. And so we're looking at it, but as I said, the ticket is very expensive. So it is a possibility, but it will depend on the financial climate.
Well, I mean, people might say, South Africa is ripe for international investors because the rand is so weak at the moment, and if they are investing dollars, euros, and pounds, they could certainly support our structures, but also gain some benefit for themselves as well. Would you not agree?
Absolutely. So I talked about the investment that's coming in on the Space Infrastructure Hub, the 4.5 billion. And guess what? Immediately when we made the announcement, there were investors from abroad saying, can we co-invest and partner with you? We've seen investors from the US, from Australia saying, can we co-invest? And so that's coming through the Department of Trade and Industry. I think the SA Invest, even the IDCs saying, can we work with you? The DTI is interested in building industrial parks. Can we work with SANSA? So there's all sorts of other investments that are cropping up from other investors based on the Space Infrastructure Hub. So you're absolutely right. Investors are looking for these opportunities as well.
I mean, it's quite possible that a certain ex-South African, I won't mention any names, might want to bring his rocket technology over here and partner with SANSA and possibly even look at launching rockets from South Africa. You never know. Anything's possible. So,
Anything.
so a little birdie on my shoulder tells me that there is a small strip within Somerset West where some of the most innovative new space technology is taking place, so much so that international space agencies are sourcing hardware and services from a handful of very talented space related businesses. Is there an intention to grow that sort of aspect within South Africa? Because obviously with SKA going on and SANSA looking at developing new projects and now collaborating with NASA, it's becoming evident that space is becoming the flavor of the month. Are you looking at developing the space industry, not just for SANSA, but in terms of the South African space industry?
Yes, that's a very, very important question. So just to put this into context, it is not the intention of SANSA to implement the space program inside of SANSA. In fact, if you read our mandate, the SANSA Act, it says that we have to support and facilitate the development of the industry to help build the industry and also help to implement these programs. So what we've done with this new investment that's coming through, in fact, 80% of this funding that I'm talking about will be spent with the industry, because we'll be contracting the industry, prime contracting on the satellite build design phase, and even on the products and services downstream. This is where we bring in the industry into the equation. So what we've done is we've set up we haven't, but we've asked the industry to self-organize. So there is an industry forum called ZA Space Inc., ZA Space Inc., that has been established. So we talk to the industry through this forum, because what we don't want, and the current climate, if you look at what's happening in the news, the fraud and corruption, we don't want to start having engagements directly with industry, and then they are contracted, and then there's questions asked. So we want to work at arm's length. So we work with our industry forum, say, you self-organize, and when it's time, we will issue these contracts that you can respond to. So there is an industry forum that's been established, and the whole intention is that we're going to be looking at centers of competence. Like, let's say we decide we want to set up optical satellite images. We want it to be built here in South Africa, because already about over 100 of these images have been exported to the UK, built here in South Africa. We've seen magnetometers or torque rods being exported to foreign suppliers or satellite builders. So there's a lot of these technologies are being exported, but built here in South Africa. So we want to leverage on that and build and expand on our industrial base, which will also serve the national needs as well.
Wow. Well, I mean, this is not really a question. This is just a comment from Estelle. As a SANSA employee, I'm very proud to see this type of presentation out there, and well done, Val. There are a lot of supporters out there for you. In fact, someone over here said, thank you very much for the inspiring talk. This is also from the Mars, thanking SAO and the SciFest team for the Mars ones, because these are for the students for the exploration and development of space. And obviously this is the SA Division 1. There are a lot of people who are obviously taking a very keen interest in what is going on in technology and space. But now here comes a tough question. Being in education myself, we need a lot more STEM literate students coming through the educational system, because if we want to bolster and support this sort of industry, we need a lot more technical people, we need a lot more scientists, we need a lot more engineers, and maths and science are not doing so well on the educational front. What sort of support is SANSA giving to boost that side of things?
Yes, so Steve, what we have in SANSA is a bursaries and scholarships program. So we support PhD and master's students. So every year we support about 50 students on an annual basis. We also, interestingly enough, there's a couple of things that are unique to SANSA. We have a student accommodation center inside of SANSA. So you might be linked to a university as an example, but you're actually supervised by SANSA staff who are actually researchers in their own right. So the students actually live on the SANSA site and they work in the SANSA offices alongside the researchers. And so that's something new. And we actually, so we can accommodate about 20 students per year on our site, over and above the other 30 which work at the university. We are currently expanding the accommodation to bring in more students. We have actually just in the process of concluding on a research chair in solar physics. It's the first research chair in South Africa that's allocated to a public sector institution. All other research chairs have been allocated to the universities. And this research chair will be based at SANSA, supervising the students and working on a new space weather center. In fact, the design for the new space weather center was released internally on Monday. It blew our minds away. It was a brilliant architect that's coming through. So this will be done in the next 2 years. So all of these interventions is about growing our own timber. We also have interns that we take on every year that work alongside SANSA staff. And there's quite a few of those. We also have artisans working at SANSA. And then we also have an outreach program. So every year we try to reach about 25,000 to 30,000 students on an annual basis. We also have a science museum in SANSA where students come in from busloads. We perform experiments for them. We train the teachers. We have a robotics initiative. So all of these things are sort of playing out on the outreach side. We also have unique partnerships. We also have mobile lab. So it's a little vehicle, like a little combi, and it's kitted with experiments. So these vehicles go out into the schools that don't have laboratories. So we conduct the experiments on their behalf so they get a better understanding of the science and mathematics concepts. So all of these things that are being done inside of SANSA or by SANSA, and there's partnerships as well. X in a Box is one example where they've now produced these little kits that are used at school level, and they've actually launched a few of these thin sats into the ionosphere, which the students actually talk to from their classrooms. So all of these things are happening. And then we also have these international partnerships. So for example, we're speaking to and trying to forge a relationship with the UK National Space Academy. And if you went to the UK National Space Academy, they have a full museum with a dome, a space dome as well inside of there. And these are the kinds of things that we're looking at going forward as well. So with the Space Infrastructure Hub, at least 1% of that is towards human capital development. So we're looking at about 30 to 40 million in the next 3 years, over and above what we currently spend.
Wow. So clearly you've got that base covered. Now, I would love to ask a whole bunch more questions, but I'm already getting the stink eye. They are telling me that we are reaching the end of our time frame. So I was asked just to remind everyone that tonight there is going to be a star party. It is a collaboration between the South African Astronomical Observatory, SciFest, and Master KG. Yes, the same guy that has brought you that wonderful video dance that has now revealed how uncoordinated many people around the world actually are. It is, of course, the Jerusalem song that many of you have heard on the radio. There will be this fantastic event. If you'd like to learn more about it, please visit astrofest.saa.ac.za, or you can visit the SciFest website, and more information will be posted on their social media. And that leaves me the opportunity to call Pran from SAAO. He is going to bid farewell and also give the thank you. So Pran, over to you.
Thank you, Steve. Good afternoon, and thank you all for having joined us for our last public talk at the virtual festival Astrofest. Let me thank our host for today's session, Mr. Steve Sherman, Now, if you're in science and science engagement, we know that getting into contact with Steve is not easy, as we see from his background. But at the same time, you always see Steve around. So I don't know what kind of algorithms you're actually using, Steve. Uh, Steve, when we finally get onto Mars, I will write a request that we name at least one country Sherman. Thanks to our colleagues at the South African National Space Agency, or SANSA, and to their CEO, Dr. Velanath and Musisami, for giving us your time today. Unpacking space science in the matter that you did was so engaging, allowing understanding from our end and everyone else the crucial role that space sciences has in South Africa and in the world. Thank you very much, Dr. Vel. And lastly, to SciFest Africa and the National Arts Festival. On behalf of our team at the SAO, a huge thank you. And I look forward to our future engagements. With that being said, thank you once again for joining us. We look forward to seeing you at the start party at 19:30 this evening with Master KG and live stargazing. On behalf of our SAO and SciFest teams, thank you very much. This has been an incredible week with great comments and lots of interactions. So on behalf of both our teams, this is us signing out. Thank you very much.